Good day, my name is Henk Cornelissen and this presentation is a follow-up on the 2-minute PICO presentation that was given at the EGU conference on the 28th of April in 2021 by me. I would like to use the coming 15 minutes to elaborate a little bit more on the preliminary datasets that we have been working on since 2019. Our team consists of William Fletcher, Philip Hughes, Benjamin Bell and myself of the University of Manchester in the United Kingdom. Our partners are at the Qadi Ayad University, Morocco and at ANSTO, Australia. As part of a Lever-Hume-funded project, we are conducting a high-resolution multi-proxy investigation of a lake sediment core from the High Atlas Mountains in northern Africa. Using sediment material as a starting point, we seek to increase our understanding of this not well-studied region in northern Africa. Other paleoenvironmental studies in the High Atlas have depended on undated pollen records or do not cover the entirety of the Holocene. So far we have gathered the region's first dated multi-proxy dataset consisting of 7 proxies that is to be used for the reconstruction of Holocene environmental conditions. The dataset is made up of sedimentological analyses like grain size analysis at a decadal resolution to measure the makeup of different sedimentological layers. Added to this, we are using elemental analysis on both organic as well as inorganic elements to better understand the composition of this site since its formation. We're also in the process of building up our palynological record, which consists of the quantification of pollen grains, non-pollen pollinimers, and charcoals, to gain a better grasp on local and regional biological signals through time. The focus of this presentation will limit itself to a general description of past environmental periods that we're increasing our understanding on. The Yagour Plateau is located in the High Atlas mountain range, due southeast of the city of Marrakesh. These mountains border the Saharan climatic region and may provide new insights into Holocene paleoenvironmental developments. At about 2,500 meters above sea level, this lake, or Ifart, is perched atop of a sandstone-rich mountain and is a closed system with no fluvial input and no permanent outflows. Around the lake there are a few small springs that we theorize provide the system with water year-round. When we visited the Ifart lake in the early summer of 2019, the water level was not higher than about 1.5 meters at the center. The flat nature of the system makes it seem that lake levels of multiple meters deep are historically unlikely. Future fieldwork will be critical in understanding the hydrology of this site more. The High Atlas Mountains form a boundary between the Atlantic climatic system to the north and west and the Sahara climatic system to the south and east. Based on this, the plateau should pick up environmental signals that are dominantly caused by either climatic system or by the interface of both. As climates change through time, so do the environments that depend on them. Environments are composed of, for instance, the local ecosystems and the regional cryosphere. And any change in the regional climate forcing may push one mode of environment into another. How easily environments change modes can depend on the resilience of the system. The drying out of a mountainous wetland system could be a gradual, millennial-scale process if regional glaciers provide the system with summer meltwater, which would then dampen the climatic effects. Likewise, a mountainous lake could possibly dry out rapidly following a few years of drought if the springs cease to provide year-round water when groundwater level drop too much. This means that environmental signals can depend on climatic factors to different degrees in different times and locations. Fortunately, the Yagour Plateau provides us with highly local environmental proxies due to its small catchment area. The almost 3-meter long core that forms the foundation of this presentation was taken with a Russian core in 2019. Its stratigraphy is characterized by many different gradual and abrupt transitions that go from organic-rich fine sediments to inorganic sandy layers. These alterations indicate consistent changes in the dominant sources of the depositional material, where aeolian deposits, coarse slope runoff, and organic accumulation are thought to be dominant factors. 3 main stratigraphic zones are identified, with an inorganic to low organic zone covering the first third of the core, starting from the sandstone substratum. The transition of this zone into the next is dramatic, in that a very coarse inorganic sand layer makes way for a thin clay layer and a thick deposit of highly rich organic material. This second zone is characterized by finer material with a lot of organic rich layers and covers the middle third of the core. The topmost final section of the core is coarser again, with many alterations. The current HDF model is based on carbon-14 analysis of 12 pollen concentrates and 3 bulk sediment samples. The deepest organic layer provides us with a calibrated age of 12,800 years before present, or at around the onset of the Younger Dryas. The current model suffers from a hiatus in a lower organic layer, up to the onset of major stratigraphic changes in the core, which makes it more difficult to reliably pinpoint the exact timing of what is likely a rapid environmental shift. Presented here is the HTAP model accompanied by the grain size distribution, the carbon contents, and the quantities of elemental iron. The main environmental drivers of this data is thought to be the depositions of fine, iron-rich dust coming from the Saharan region and deposition of coarse inorganic local sands that are rolling down the slopes around the lake. A third driver seems to be episodes of stable organic accumulation, producing the 7 to 8,500 year old deposit of black material. A current working hypothesis is that around 8,500 years before present, a rapid environmental transition to weather conditions took place at this site. This transition followed climatic forces that were conducive for a stable accumulation of organic material. Other periods with varying rates of influx of Saharan dust can be seen since this change took place. Here, the correlation between proxies that may be driving the aeolian deposition rates is visualized using Z-score standardization. These four proxies of grain sizes to elemental titanium to calcium ratios and elemental ion content to linear magnetic susceptibility may help us understand more about periods when topsoils from the Saharan flatlands were transported up into the High Atlas due to, for instance, climatic drying events. Parallel to the sedimentological proxies, we're also currently developing a high-resolution pollen proportion dataset to gain more insights into the local and regional Holocene vegetation. The pollen grains from trees are thought to come from well-mixed regional pollen grain, and the aquatic pollen species likely reflect much more of a local signal. Skipping over the HTAP model, we've got a quantitative plot with the calculated amount of pollen grains over time and stacked diagrams indicating the relative proportion of trees and shrubs, herbs, aquatics, non-pollen polymorphs and microcharcoals, respectively. The final graph indicates the amount of microcharcoals, which should reflect local fire events. The terrestrial and aquatic pollen proportions see an abrupt increase after 8,500 years before present and go through periods of stable and erratic conditions until the concentrations come down to modern levels about 600 years before present. After 8,500 years ago, we see the emergence and later on the demise of coniferous trees. All tree species diminish sharply by about 4,000 years before present. Cyperaceae are known as sedges and are a lake-margin aquatic plant taxon. Periods with increased Cyperaceae counts may reflect shallow lake levels, as opposed to a dried-up lake margin. The microcharcoal counts may correlate with the availability of burnable biomass, and could for the majority of the Holocene be attributed by fire events caused by, for instance, seasonal thunderstorms that the region is known for today. The large fire events that are associated with the previous 4,000 years before present may be correlated to the arrival of Neolithic peoples to the plateau. A timeline that seems to agree with regional anthropological studies and local petroglyph studies. When comparing our datasets to earlier studies that provide insights into regional climatic information, we see that our different sedimentological and paleoenological zones are particularly in tandem with changes in regional climate. On this slide we find data from 3 climatic studies. Shah et al. Produced a model in 2019 for Western Atlas precipitation rate over the past 12,000 years by analyzing oxygen-18 isotopes from a speleothem. Tournier et al. Produced a model in 2017 for precipitation rates over the past 19,000 years by analyzing leaf wax isotopes from a series of marine cores off the coast of Northwest Africa. The final graph is a model of changes in total solar irradiation over the past 9,000 years by Stein et al. In 2009. These 3 literature datasets have been standardized through set scoring around the mean and include a smoothed line to indicate the trends. Negative values are associated with higher levels of precipitation in the 2 precipitation plots and lower levels of global solar irradiation in the solar plot. The periods indicating increased precipitation by Shah et al. In 2019 and Tournier et al. In 2017 could have meant that the Yagour Plateau switched from a drier landscape reflecting current conditions to a much more lush and vegetated landscape during the Holocene climatic optimum. The first radiocarbon-dated late-glacial and Holocene environmental record from the High Atlas reveals that there is an incredible amount of future potential to this site relating to Holocene reconstructions. Even at this preliminary stage of interpretation, it is clear that the record reveals significant influences of long-term and millennial-scale climate changes on the vegetation, hydrology and geomorphology of the Yagour Plateau. The paleoenvironmental signals presented here are thought to have been driven by regional climate systems that dictate precipitation rates and local factors such as the supply of moisture through local snowmelt. This presentation follows the first look we have had on our datasets as a whole. In the near future we hope to cover these and other subjects in a more in-depth approach.